Anybody has syllabus sign-in sheets they still need to get rid of?
I think Adrian did one. No, I didn't.
I would take those. I think probably we're almost all good. So the quiz you guys just did, when I go and look at these, my hope is that almost everyone knows what to do with the first question and can do that correctly. The second one, I would hope that most of us recognize kind of what needs to be done, even if we make some stumbles as like the getting it done part with our algebra, but recognize what you would have needed to do. And the last one, kind of the same story. It's like hopefully you recognize like what you would need to do here, even if you make some stumbles along the way. That that you're able to, at least on questions 2 and 3, recognize like what to do, even if you can't get there all the way. I think is a good spot for right now. Again, we're not testing tomorrow. It doesn't have to be perfect right now. The homework quizzes are just kind of like creating some incentive for you guys to engage with the material maybe a little bit more deeply than you would on a homework setting. And for me to get you some feedback relatively quickly about like how things are going, you to see the kinds of questions that I would write to put on tests. It's not meant to be like a formative thing. It does not need to be perfect. Like you can get 1 question out of 3 right, and if the other ones are pretty close, that's still a 9. And there'll be a bunch of these. They end up kind of all evening out. There's some drops. It's the smallest percentage of your score, so it's nothing to get like, make a big deal out of. It's more just, for me, that force you to kind of engage with the material more deeply than you would for a homework to prepare for something like this. And again, this would probably be about as long as they would get in what you guys took to do that. Where again, the idea is that this is quick. It's not super thorough. It's usually limited to like 1 or 2 ideas just to get us, get me an idea of kind of where we're at, give you an idea of like what is the kind of things that I'm looking for. But I think those are pretty fair examples of the kind of limit questions that I would ask on a test or quiz setting. And if that felt reasonably comfortable, I think you're in probably a pretty good spot with like, okay, I can deal with an analytical limit like that, or I knew what to do even if like, I knew I made some mistake in there algebraically or something, but like, I knew what I was supposed to do, and just kind of like, got to a part where it's like, oh, I think I screwed up adding the fractions, or I screwed up, rationalizing the denominator if I got to FOIL something out correctly, or whatever, like mistakes. All right, so today we're going to talk about our next topic. So 2.4 I listed on there. It's the precise definitional limit. We gave it already. That was the epsilon delta stuff where I kind of like talked about what that meant. We're not going to do any of that in practice because it's beyond the scope of this class, and it's even beyond the scope of like the BC class. It would be something I don't think you'd encounter until you're like possibly at like the calc 3 stage where they'd be asking you to prove a limit using the epsilon delta definition, which I just don't think is worth the time right now to like get good at a skill that nobody's going to expect you to have, and by the time you need it, you won't probably remember what to do with it anyway, so we're going to just kind of bypass that. Today we're going to be talking about continuity. So you guys have talked about continuity already in probably algebra 2, through calculus, and we talk about like a function being continuous. We talk about it being able to, you can draw it without having to pick up your pencil, right? Does that sound about right when you guys encountered that? What we're going to do now is we're going to formalize that definition to be something that you can prove. Not just like, well, I can do it or not, and like I need to generate a picture to do it. Now we're going to be able to prove it. We're going to be able to generate that, prove it symbolically. No graph required, no picture required. So we first have to kind of think about what it means to be continuous at like one point. So for a point, or a function to be continuous at a point, the function has to come into that point, be defined at that point, and then exit out at that point. Everybody kind of agree? So what that's basically saying is the left-hand limit has to exist, the right-hand limit has to exist and be the same thing, and then the function also has to be defined there as well, and the same thing. So in general, what we're saying is that our function is continuous at some value a if the limit as x approaches a of f of x is just equal to f of a. So if you combine this idea with what we talked about in section 2.3 when we talked about analytical limits, we know right away that polynomials are continuous across their domain because we could do direct substitution for that limit, that the limit as x approaches a equals f of a for polynomials, and for rational functions inside of their domain, right? That those are continuous over their domains. So for a rational function, you have like two continuous parts of it that would be like separated by an asymptote, but it has like a continuous part to it. The function in general is not continuous, but it has like a continuous part. Everybody okay with that idea? Okay. So, basically we just said this all in words and just kind of talked through that. So those notes are there. If we look at this picture, we ask what values or what numbers is f discontinuous and why. So if I look at this, how many discontinuities do we see? Is it too small?
Yeah.
You should see 3 discontinuities. They are at 1, 3, and 5. So 1 is a discontinuity. It fails our definition of continuity because f of 1 is undefined, which does not equal the limit as x approaches 1. You agree? 3 is a discontinuity because the limit as x approaches a doesn't exist because the left-hand limit doesn't equal the right-hand limit. And 5 is a discontinuity. It fails the definition of continuous because f of 5 does not equal the limit as x approaches 5. Both of them exist, they're just not equal. So we've seen 3 different ways that we can be discontinuous, right? F of a doesn't exist, the limit doesn't exist, or the two are not equal. Everybody feel good there? So that's the takeaway when looking at this. That's what we want to see, is that you can fail that definition of continuity kind of in 3 different ways. All right, let's take a look here. So here we're asked to figure out where each of these functions are discontinuous. So for the first one, for A, David, 2. It's a rational function, so it should be continuous everywhere except where the denominator is equal to 0. We can see that's very clearly 2. It does not matter even if I can factor and reduce the x minus 2 out of there. Right? That discontinuity stays. It's just now removable rather than a vertical asymptote. You guys remember that from pre-calculus and algebra 2? Okay. So for B, it says f of x is equal to 1 over x squared for x not equal 0. And it's equal to 0, and then it's equal to 1 when x is 0. So here we have f of 0 definitely exists, right? Everywhere other than 0, the function is clearly continuous, right? Because we have a rational function. The only thing in the domain that's going to be a problem is at 0. But what's the limit of f of x as x goes to 0? If I look at 1 over x squared, the graph of that's going to go like this, right, as we go to 0. That limit as x approaches 0 is positive infinity. But f of 0 is 1. That means we have a discontinuity there at 0. How about C? So we have this rational function everywhere except for 2, and then it's equal to 1 when x is 2. So we know this limit exists, right? And we know the function is defined at 2, and we know it's good everywhere other than 2 because it's a rational function. So what I need to check is to make sure that the limit as x approaches 2 of this, I need to check to see if that's 1 or not. Pretty good with that? So to do that, we'd factor and reduce. And then we can direct substitute that. We get 3, which is not what f of 2 is. So that guy's a discontinuity. And then we're not going to do D. This funny notation here, I think, is that the floor ceiling function? I forget what the notation is. It's one or the other. So like the floor ceiling function means it just basically round up or round down. So like if it's the floor function, you know, everything rounds down. So like 0.1 rounds down to 0. 0.2 rounds down to 0. 0.957 rounds down to 0. 1.5 rounds down to 1. 1.8 rounds down to 1. It just basically takes you the least, the next integer down. That's the idea. I think that's what this is. So this guy has infinitely many discontinuities at every integer value, right? Yes, exactly right. And the greatest, or the ceiling function would be the same thing, but it's shifted 1 unit to the right. So like the ceiling, like 0.1 would round up to 1. You know, so it's the same graph, it just shifted 1 unit to the right. Either way, I can't remember if that's floor or ceiling with the notation there. Either way, it has infinitely many discontinuities at every integer value. Beyond the scope of something I would ask you to do, but it creates like a nice example where you don't have to use a piecewise function to create a discontinuity you can't just look at and see. Does everybody feel okay about what we did here to check? So in general, if I'm checking for discontinuities, and it's a piecewise, I look for any discontinuities in the piece, and then where they junction together, right? So I have to check inside each piece, and then where they junction together at. Does it feel okay? So again, we have some examples of discontinuities. So these are the pictures that we saw before. This is floor, by the way. I can tell now from the graph that's the floor function. So again, you know, removal discontinuity. You know, we have an asymptote, but then we replace it with a specific value. Here's the removable, but we have like a jump. Here's just like a bunch of jumps. So those are the graphs of what we looked at before that we did analytically. Notice that we can do continuity without a picture at all, right? And that's the takeaway from what we're doing here, is that there's a way to do continuity without having to rely on looking at a picture. So this leads to a question, you know, like what about something like y equals the square root of x? What do we say about that point? We want to say that point is continuous, correct? Because it's part of something we can draw with one stroke of a pencil. We want that point to be in our definition of continuous. The problem with that point is it doesn't have a left-hand limit, because the function doesn't go into that point. Does everybody see that? So what we want to say then is that when we say continuous at a point, if the function doesn't have another side to it, we only need to look at if the left-hand limit or the right-hand limit, per se, is equal to f of a. So that's what we're saying. We say a function is continuous from the right if the right-hand limit is equal to the function, or continuous from the left if the left-hand limit is equal to the function. And we say that a function is continuous on an interval if it's continuous for every number on the interval, and at the endpoints, it's okay to just be continuous from the corresponding side. That would be fine. We don't have to say it's continuous on the interval. Is everybody okay with that idea? So we just adjust our definition to say something like this still counts as continuous at that point at the end, because we look at it and it's like that's what we want it to be, right? We just adjust our definition to include those cases. And we have to check to make sure nothing weird, degenerate, sneaks in with this function and doesn't. But that's the idea. Okay. So this example now gives us a function, 1 minus the square root of 1 minus x squared. And we want to show that that function is continuous on the interval from -1 to 1. So I'm going to do 3 continuity checks. I'm going to check the endpoint -1. I'm going to check the other endpoint +1. And then I'm going to check an arbitrary value between -1 and +1 for everything in between. And I can't check everything in between because there's infinitely many values between -1 and +1. But I'm going to pick like an arbitrary, like A, from the open interval from -1 to 1, and show that any A from that interval is continuous, which knocks them all down. So are you okay with that plan? Let's see. So I can just direct substitute this one, right? When I do that, I get 1. And again, I can just do a direct substitution here. I get 1. And if I did direct substitution on that, then obviously I have continuity there, right? Somebody feel okay with what I did? And I skipped showing the plugging it in because we're big boys and girls and we can check those in our heads, right? So now I'm going to take an A from the open interval from -1 to 1. Again, just using direct substitution, I've shown that those are now good to go. And really, I guess I should make this one little adjustment. Should probably say left-hand limit, right-hand limit on the endpoints. But that's the idea. Is everybody okay there? Okay.
Open like the actual value between -1 and 1.
You want to do it arbitrarily, because if you pick an actual value, just pick 0, then all you've done is shown continuity at 0.
Okay.
But you haven't shown anything between 0 and -1, between 0 and +1. If I just pick an arbitrary value and call it A or B or Z or whatever, now I've done it for all the values.
Okay.
So it's the same idea. Yeah.
I'm just confused on what's like the final answer for this? Because if you put check marks for like
So it's the question says show, so the final answer is all of this work. So we've shown it for the endpoints and then shown it for everything in the middle. So now it covers the entire interval.
and show this is
Continuous. And again, for continuous, it's showing that the limit as x approaches a is equal to the function of value in it. That's the requirement. Adrian.
So for like the one in between, is there like any way that it could be wrong or not?
Sure, yeah. You could have, I mean, if I ask you to show that something's continuous and it isn't, right? Like, you have something in there that doesn't work.
Yeah.
Um,
Like if it's just a like if
Yeah.
it is
there's not much to do. Yeah, that you are right. And that basically all you're doing is plugging stuff in and direct substituting. You know, the only way that this would possibly get ugly is if you have like an indeterminate form in the limit. Like here, my limit can't have an indeterminate form because it's just there's no fraction or anything on it. So it's like we're all in the clear. But like, you know, if it was like this same thing and it had, you know, like over x, now all of a sudden at 0 you have some issue. You know, so it just kind of depends on what the function looks like and how messy it's going to get. But if it's something that's like, you look at it, it's like, well, that's a radical function that's continuous over its domain. Like I know that because we studied all these continuous functions in like algebra 2 and pre-calculus. You shouldn't get a lot of surprises, right? If it's something weird, it's like, oh, that's a weird piecewise function. Now you might have to be a little bit careful. But if it's something that like you recognize and know is continuous, we're going to get to the good stuff here in a minute. Where some of these things you can just say it's continuous because of the type of function it is. So we have some theorems now that'll be useful in showing continuity. So if you have two functions, f and g, that are continuous at some value a and some constant c, then the following are also continuous at a. So the sum of the two continuous functions, the difference of the two continuous functions, a constant multiple times a continuous function, the product of two continuous functions, and the quotient of two continuous functions, provided that the denominator is not 0 at that value. Which is awesome, because if you have, like, show that x plus cosine x is continuous, well, that's a pain, unless you think about it as, can I show x is continuous? That should be easy. Can I show cosine is continuous? That should be easy. The sum of two continuous functions is now continuous. Smooth sailing. Does that make sense? So, new theorem, it says a polynomial is continuous everywhere. So that you can quote. You need to show something's continuous and it's a polynomial, or even a piece of a piecewise function, some piece is a polynomial. You know it's continuous over its domain. So you get that for free now. All you have to do is say it. Like it's continuous here because it's a polynomial. You have to justify that it's a polynomial. You can look at it and just say it's a polynomial as long as it is. You can't say it's a polynomial if it's not, but that's enough justification. Any rational function is continuous wherever it's defined. That is, it's continuous on its domain. So again, as long as you're talking about something that doesn't cover, or an interval that doesn't include an asymptote, that rational function is going to be continuous as long as it's defined there. Everybody feel okay? I'm going to skip this example because I don't really understand why it would have been put there, because it's just a direct substitution problem. I don't know what I was thinking when I included that. Here is the the big one though. So we had our definition of continuity. This is the big theorem, along with the add, subtract, multiply, divide, scalar multiplication of. The following types of functions are continuous at every number in their domain. Polynomials, rationals, roots, trigonometric, inverse trig, exponential, and logarithm. All the function types that you've studied in your high school math career to this point are continuous over their domains. You get all of them for free. That's super useful, particularly if you're dealing with showing a piecewise function is continuous. You should probably get the only things that then you have to worry about are the spots where it's linked together. Because you can probably just quote this theorem for piece 1, piece 2, piece 3. Oh, this piece is continuous because it's a trig. Or this piece is continuous because it's the sum of a polynomial and a logarithm. And this piece is continuous because it's a radical, and then all I have to do is check, the 2 points are they end together, or they link together. And now it's turned into checking infinitely many points just up to 2. Because most of it we get for free. You gotta say it. You gotta say it. So if I look at example 6, it asks where the function is continuous. If I look at the 3 pieces that make up this function, I have a logarithmic function, an inverse trig function, and a polynomial. You see that? All of which are going to be continuous over their domains. Do you agree? And because they're just added, subtracted, multiplied, or divided together, this thing will be continuous over their constituent domains. Right? If I just look at all the domains of these 3 things and intersect them together, that should give me the domain except for when the denominator is 0. So I'm going to pick up some extra discontinuity from that. But that's it. So let's look at the domains of each of these. What's the domain for the natural log? Or really any log of x. Doesn't matter that it's the natural log. It could be log base 2, log base pi, whatever. Has to be greater than 0. Thanks, Anthony. Yep. And you don't have to write the plus sign on your infinity. I always do because it's just habit to make sure I write the minus when I need the minus. If I just write a sign in front of infinity every time. Is everybody good there? Okay. What's the domain for tan inverse? All real numbers is correct. Again, the way you'd want to think about, if you weren't sure, if you remember what the graph of tangent looks like, it looks like this, right? Hopefully you can remember at least that much. And then if I just wrote or flip this across the line, y equals x. That's the graph of tan inverse then. The domain there is clearly all real numbers, right? It's going in both directions. Can I erase this? It's just, again, for the trig stuff, I try to if you didn't have it memorized, what would you do with it? Or how would I think about it? And try to connect it to something that, like, hopefully is basic enough that you do kind of remember what it, like what does the graph look like? Or what is the basic thing that I can break this maybe complicated memorization thing into, that it's easy to work my way through it if I'm stuck on a test setting or something. I'll try to go out of my way to model that stuff, especially for the trig stuff that was a lot of memorizing that we hope we still have, but in reality I know we don't. So, like, what do you do if you don't remember? And again, polynomial is all real numbers. But the domain, we also get a bonus because we have a denominator, right? What am I going to lose from the denominator? One and negative one. Everybody feel good? So if I take the intersection of these domains, what do we get? So that would be the union. So if you think about it this way, if you're not sure, if I draw these three domains, that's like my three domains, right? As if they were number lines. The intersection of these is going to be the stuff that overlaps all of them, which are just the values greater than 0. You see that? So again, like if you're union intersection, just like we're just looking at the overlap. What numbers are okay to plug into all three parts? Is everybody okay there? And again, I'm doing this not like the most efficient way possible. What I want to do is like give you some conceptual understanding of what we're doing. So you can't answer just this one question, but any question like this. Trying to provide you a framework of thinking about this that you can carry forward into any kind of problem. So far, so good? So if I take these, I'm going to have that. But now I have to lose from this -1 and +1. Now -1 is fine because it's not in there anyway, right? So that doesn't matter. But net +1 is. So if I just take +1 out, I have the stuff from 0 to 1 and the stuff from 1 to +1. And I'm done. Does that feel okay?
That's it. Is it still in there?
Well, the parenthesis means it's not included, right? So it's everything up to +1 and then everything after +1. Right? Is the way you want to read that symbolically. Does that feel okay, Tyler?
Would you use a bracket on 0?
No, because the domain for a logarithm is logarithms have to be a positive value. So if that was instead like square root x, then yeah, that would get a bracket. Because that's a function where like you can square root non-negatives, so 0 and positive. Logarithms are only positives though. Does that feel good? Yeah.
Why did you have the -1?
Because it's not in the domain anyway, right? The domain is only things greater than 0.
Oh, okay.
So -1 doesn't even matter. It's not even in the domain of the 3 anyway, so I don't have to worry about it. I mean, I could take it out, but it's not in there to begin with.
Yeah.
Does that feel okay?
Yeah.
So again, you can get distractors like that. That's like, oh, I get, a 0 denominator for something that's not in the domain anyway. Well, I just ignore it. It doesn't do anything. Because I already couldn't have that value before. So just because I divided, now I can't have that value. It's fine. I didn't have it to begin with. Does everybody feel okay on this? Notice that this is just the sum difference quotient of continuous functions, right? So because of that, I can direct substitute. So it's just going to be like 0, 1, plus 2, right? That's, no, 1, 0, plus 2. So it should be 1/2. So that's my justification for being able to direct substitute. You remember before when we had the direct substitution, it was very specific. It's like only into polynomials and rational functions over their domains. What you have now is that you basically can direct substitute into anything you want all willy-nilly. As long as you're like direct substituting into a continuous, like a value that's part of the continuous function, you're good. And then remember, we hinted at this idea before that we hope this is always true, and I told you it's not, but it's almost always true. So it says if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of f of g of x is equal to f of b. Or in other words, we can push that limit inside of a function composition. So like our canonical example of something like this is you have something like this. It's like I don't love this. You can do stuff like that and push it inside of the function composition. But that's the idea. You have to be a little bit careful that like the domains work out. And I'll show you a graphical example here in a minute. Because it's much easier to generate those examples where this fails graphically than it is algebraically, like symbolic with like function definitions. Quite difficult to come up with something. Graphically, it's pretty easy. So if we look at this example here, if I try direct substitution, what am I going to get? 0 over 0, right? Or sine of 0, arc sine of 0 over 0, which is still a... So there's a 0 over 0 in there, that's an issue, right? Do you guys remember arc sine is the same as sine inverse? Right? Or no? So we can do that. What are we going to do with this now? What's that? Alice? You said something I wanted. Go ahead. It's okay to be wrong. You can multiply by a conjugate. That's certainly the obvious thing that you do here. And that would be correct. That'll work. Can I make a suggestion of some way that's even easier to think about this problem than that, though? When I look at this, what I look at or what I see is like a difference of two squares. Oh, bless you. I see 1 minus x. That really looks like 1 minus square root x times 1 plus square root x. Right? Where like 1 minus x is like 1 squared minus square root x squared. You see why I wanted to do it that way? What else would you suggest would absolutely work? It's not really much simpler than this, other than like, I can do that reducing in my head if I think about it that way. Where again, not the end of the world, not a huge advantage, but like, these are things that are potential shortcuts and backdoors that I want to show you along the way. Like, oh, this is a clever way of thinking about this that could potentially be useful later on, or when it comes to AP test time, where time is like really a factor. If there's something I can do in my head in 3 seconds versus 45 seconds to write down, those seconds all add up. And it becomes like giving us, it's the ability to take 5 minutes on some problem that was difficult to figure out that you didn't have any idea what to do with it and still have time to finish the test kind of thing. So you could do this. So when I do my direct substitution, I get 1/2. And arc sine of 1/2 is in radians, because we're in calculus class, 5/6, 30 degrees. So it's the triangle with the low height, so it's going to be the low base angle. Theorem 9 is another function composition where we're just preserving continuity through a composition. So if f is continuous at A and g is continuous at f of A, then f of g of x is also going to be continuous at A. So again, you just have to make sure that everything is tracking through, that the domains are lining up in the right way. I don't want to do this. We're going to continue on. I want to talk about the intermediate value theorem, which is something that you'll definitely use and we'll definitely talk about more so than continuity through a composition. So the intermediate value theorem is one of these theorems that you will need to quote by name. You'll need to demonstrate that the conditions are satisfied and then be able to use the conclusion to state something. This is something that I guarantee will come up and be used on the AP exam. Most likely in multiple locations, both as a multiple choice question and then again as a free response question. Almost every single exam I've looked at uses this theorem at some point in both multiple choice and free response sections. So the intermediate value theorem says that suppose f is continuous on the closed interval from A to B. When students use the intermediate value theorem, the most common mistake they make in setting this up is they forget to demonstrate that f is continuous, which is mostly just saying f is continuous because it's a polynomial, or the sum of continuous functions, or, something simple. It all takes almost no effort. Or even if it's not a continuous function, it's continuous over the interval that we need it in, right? Even if it's a rational function, it's not continuous over all real numbers. It just has to be continuous from A to B. And we know a rational function is continuous, over the sections of its domain. Like in between the asymptotes, it's continuous, so. Okay. Continuous on the closed interval from A to B. And let n be any number between f of A and f of B. So n is like a y coordinate. F of A and f of B are y coordinates. Right? Those are outputs. If n is in between those two specific outputs, as long as those two y coordinates aren't the same value, there exists some number, some x value c, where you plug that x value into the function and that value n comes out. And this picture below is just kind of our justification for why this theorem works. Right? So here's my A and B. Here's my f of A and f of B. Here's my n. If I try to start here, and anything I draw, and I have to end here, and I have to get there without picking up my pencil. No matter how I try to draw this, I have to cross that value for n somewhere, right? As long as the thing has to be continuous, that it has to be connected, it's got to cross that value for n. Now, it's not going to tell me what that c value is. It's not going to tell you what is the x that gives me that. It just tells me that there is one. You could find it if you wanted to. Everybody okay? So this is an existence theorem. It just is going to prove that something happens. Doesn't tell us how to make it happen. Just says that this has to be there. How do you find it? I don't know. Theorem doesn't help with that. It's probably just a solving problem though, right? All right. Example 10 says, show that there's a root of the equation, blah, 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 equal to 0, between 1 and 2. So when we're talking about the root of a polynomial, what you're talking about is a 0, right? Is everybody okay with that? Does it ask to find the root? No, the directions say show there is one. Now, could I spend my time finding it? Maybe. How did you find roots for polynomials before? You do that like crappy synthetic division stuff. Hope that there were rational zeros so you could do the synthetic division. You're not guaranteed that if this is a no calculator question and there's no rational zeros, I don't know what you're going to do to try to solve it. But that doesn't matter to us. If all we need to do is show there is one, we're going to use the intermediate value theorem. So I'm going to say let f of x equal the function. I'll say f of x is continuous because it's a polynomial. I note that f of 1, since we're interested in the x values 1 and 2, and maybe I should say continuous everywhere, specifically on that interval from 1 to 2. But f of 1 is 4 minus 6 plus 3 minus 2, that's negative 1. f of 2 is 8 times 4, that's 32, minus 4 times 6, that's 24, plus 6 minus 2, so that's 38, minus 26, so that's 12. So I'll say since negative 1 is less than 0, is less than 12, the intermediate value theorem, I abbreviate that just IVT. You may do the same. The AP will accept that as an abbreviation as well. That is pretty universal. So the IVT states there exists, if you're fancy, the fancy math symbol for there exists is the backwards capital letter E. You're welcome to use that if you like. You don't have to. You can just write there exists. A C from in between 1 and 2 such that f of C is equal to 0. So the two conditions that I need to use the intermediate value theorem, I need the continuity, and then I need that I found, that the endpoints of the interval I'm working in, the value I'm looking for is in between the endpoints, right? Because this is, that's f of 1, and that's f of 2. So those are the two conditions I need to satisfy in order to quote the intermediate value. And then it just spits out that there is some x inside the interval in question. When you plug that x in, you get the desired y value out. And again, the 0 is like our n, right? Because that's the value we need the function to have. It's like the cap n from the theorem. So at this point, we have two theorems in this test that we want to be able to quote by name and use effectively. Intermediate value theorem, and previous to this was the squeeze theorem. Those were the two that we want to quote by name. For your homework quiz for next time, you should be able to show continuity at a point. If I give you a function, you should be able to show continuity at a point, and then you should be able to show continuity across an entire function. So use the pieces that we have before, that the sum, difference, product, quotient, scalar multiple of continuous functions is continuous, along with our continuity at a point or whatever, to kind of piece those stuff together. But those would be the two types of questions that I would worry about, nothing else. I don't worry about any domains or anything else. Just showing continuity for a function and at a point. How do you guys feel? It's okay? My plan for next class, we'll do some specific intermediate value theorem and squeeze theorem stuff. And I want to show you some function composition examples where we can't just push the limit into the composition because the domains don't work out. And when you can still say something about that situation when you can't. So look at some graphical examples next time. But that's my plan, so there won't be any real new content next time, it'll be another, let's kind of settle in and make sure we understand these couple of topics. And then we'll kind of keep on moving forward after that. But we're nearing test time, so there's not a lot more content that we're gonna do before our next test. Just to give you a heads up, I think I have one more new topic to cover before test time, having to do with asymptotes, which we've already kind of done. So it should be relatively straightforward. Is everybody cool? How do you guys feel? Is it still going okay?
Yeah.
You'll tell me if it starts going bad? Alright, everybody feel like this is going, you understand what we're doing though? It's okay? Maybe? Alright, cool. How did the homework quiz go?
Easy.
Well, okay.